Hello. Today we will discuss about magnetic resonance imaging, or it is also known as nuclear magnetic resonance. So this is also one non-invasive method of imaging technique or medical imaging technique. Here you can see uh, one picture of one MRI machine where there is an MRI gantry into which the patient has to lie on this table, and that he has to enter into the tunnel which actually producing a magnetic field. Inside that, the images will be taken, and through a computer software those are shown on the display. So we'll see how this non-invasive method will work using the technique of magnetic resonance. So our body is almost 72% of water. Every tissue contains water, and water molecule contains hydrogen atom. So we can say in our body 80% it consists of hydrogen atom. So each hydrogen atom, it has a single proton, and we know that it has no neutron inside this nucleus, and this proton is revolving or spinning, as we previously know that there is a spin plus half and minus half. So this spinning of these protons will create the, it is just due to this spinning we can, it is just like an current, a current in a circular path, which will create one magnetic field or magnetic dipole. So that means each hydrogen atom is associated with one magnetic dipole. So this is the fundamental concept upon which the MRI technology depends. Now we'll see one by one. The magnetic resonance imaging technique, it uses the radio frequency region, because previously, as we have seen in case of your X-ray and CT scan, the energy source is X-ray, which is very high frequency, and it has that has the capability of ionizing our tissue. But in this case, this imaging technique in our magnetic resonance, RF region or radio frequency energy source has been used for imaging. So this is one advantage, because these radio frequency, they are not ionizing in nature. They will not create ionization in our tissue, and so they are comparatively safe than those X-ray and CT scan. Similarly, patient is placed in an external magnetic field which causes the magnetization of protons of hydrogen atom in the body. As I have said just right now, that our body is of 80% of, it contains 80% of hydrogen atom, and each hydrogen atom contains a proton, and the proton, due to its spinning property, they are considered as a magnetic dipole. So but they are randomly aligned. You can see here these are protons, they are randomly aligned. These magnetic dipoles, each magnetic just like one bar magnet, north and south, they are aligned randomly. So when our body is placed under a strong magnetic field, like as it is shown, it is the north pole and the south pole of this magnetic field, then these protons or these dipole moments, they will align themselves in a particular direction, as in either in parallel, as it is your north and south, or in anti-parallel. This is like for this one, this side is south and north. So either parallel or anti-parallel, they are aligning themselves. This process is called magnetization of proton. So due to magnetization, these protons align, and the process about the external precedes about the external magnetic field. So this precision, it is one event or it is one phenomenon that will occur under the influence of this external magnetic field. Now a radio frequency pulse, once they have aligned, so after that one RF signal or RF pulse that has to be sent at resonance frequencies transmitted into the patient under a controlled condition. And this RF signal, they will misalign or they will create disturbance to this alignment, and when it has been withdrawn, then again this aligned, this proton, this magnetic dipoles, they want to regain their original state having lower energy, or they want to come to its lower energy state by radiating this RF signal. Those RF signals has been captured through an antenna or through a RF receiver, and those contains the meaningful information, and from that current which has been captured through that receiver, meaningful image can be constructed using the computer. So due to the resonance condition of this individual proton responded by the emitting a radio frequency signal. So this is called nuclear magnetic resonance or signal. So this signal has been captured. Now you mark the anti-parallel and parallel, these alignments, they have a difference in the energy that can be defined in terms of E is equals to h nu in that term, as we know previously. So we'll see later what is this equation, what is the gamma, and what is about this 42.58 megahertz per Tesla per proton. We'll see one by one in the later slides. Now if a single proton which is spinning, now if it is under the influence of the strong magnetic field, what happens? They are aligned themselves in a particular direction, no doubt, but they are not stand still, or they are not cease their rotation. They are rotating, the spinning is going on, this is the spin is going on around its axis, and with a wobbling effect, like they are moving like a rotor. So they are moving in the particular direction, but they are not stand still. A proton has a spin, and under the influence of this, they align themselves in a particular direction, but they are not still. So a spinning top, it is just like a spinning top which is hit, performs a wobbling type of motion. Wobbling means they are spinning in a particular direction. So it will just like one cone. Okay, so it is moving in a particular direction under the influence of this magnetic field. Proton is a strong magnetic field also show this type of motion, which is called precession. So this wobbling motion under the influence of the strong magnetic field is known as precession, and they are also moving in a particular this cycle of rotation. If it starts from this point, it will take some time to reach again at this point. So this cycle is considered as the frequency of this precession. So we call that precession frequency, and this precession frequency, it depends on the magnetic field strength of that external magnet. The preferred state of alignment is one that needs less energies. That means always it will try to remain in a lower state of energy. So more proton are on the lower energy level parallel to the external magnetic field, and less very negligible protons which are anti-parallel to the applied magnetic field. Now this precession frequency, this speed can be measured as a precession frequency, at which this is the, you can mark here, if this the Z means the direction of magnetic field, external magnetic field, if it is B naught, and here you can mark this proton, single proton, which we consider as one dipole moment. It is spinning around its axis, and it is not straight, it is not freezed, it is also moving with time. It is also moving with time, like it is moving like this. Okay, sometime it will be at this position, sometime it will be at this position. So it is moving continuously. We call it a wobbling action. So this rotation also coming under or considered as one frequency. We call that precession frequency. That means how many times the proton precedes per second. This precession frequency is not constant because it depends on the external magnetic field. So you can mark here the external magnetic field, it will affect the precession frequency in which the proton are placed. The stronger the magnetic field, the faster the precession. That means if we increase the magnetic field under the influence of which this proton is aligned, then the speed of rotation will increase, or this frequency will increase. So this relation is expressed in terms of one equation that is called Larmor equation. Larmor equation says that this frequency is related, it is directly proportional to the magnetic field or external applied magnetic field. Here they are related to one parameter, or that is one constant, that is called gyromagnetic ratio, which has a value of 42.6 megahertz per Tesla for proton. Now resonant frequency or Larmor frequency, what does it mean? We have seen precession frequency. Precession frequency means when we place that body or patient, the proton inside our body, they are moving with a particular precession frequency depending upon the external magnetic field, right? Now at this magnetization is in direction of either longitudinal to the external magnetic field. It is also called as longitudinal magnetization. So that means you mark here, if we place the body under the influence of this external magnetic field, what happens? some are parallel to it. So, these are different protons, they are aligned in a parallel direction to the magnetic field. Some are anti-parallel in nature. So, this parallel and anti-parallel, some of them will cancel this magnetization, they will cancel. So, remaining magnetic dipoles are in a particular direction. They will add up to give rise a resultant magnetic field in the particular direction. So, that is as it is, you can mark as it is in the same direction or it is in the z axis. So, we can call it as a longitudinal magnetization. This is called longitudinal magnetization because it is perpendicular to this plane. Okay. A short burst of some electromagnetic wave. Now, if we apply some electromagnetic wave which is like this, a short pulse will given. Let me draw it again for you. So, let the electromagnetic wave is like this, a short pulse, then again there is no pulse, then again repeated. So, this pulse is repeated. So, when this RF signal, this RF pulse is applied, what happens? Some of these protons or some of these magnetic dipoles, they will align themselves in different directions. Some will fall in this direction, some will fall in this direction. Okay. So, in that manner, now what will happen? It will gain one, this perpendicular or this longitudinal component will reduced in nature, it will reduce the strength and it will develop some in another magnetic field direction in the same plane or in the transverse plane. So, two things will happen. One is there is a reduction in this longitudinal magnetization strength and there is one development of this transverse magnetization. So, this will happen once we apply this RF, external RF signal. So, this Larmor equation gives us the necessary frequency of RF pulse to send in. So, at one particular pulse, the purpose of this RF pulse is to disturb the proton because proton is here. Once this RF pulse is applied, this proton may move to this particular plane which are placed or peacefully precessing in alignment with the external magnetic field. Previously, they are moving in this direction, but once the RF signal is applied, so they will move in different directions and disturb from their original or resting state. The energy exchange is possible when this proton and the radio frequency pulse have the same frequency. So, that means energy exchange between this proton and the RF signal which has been applied here, that will occur when these two have the same frequency or that process is called resonance, and this resonance frequency is known as Larmor frequency. So, that means we can say at Larmor frequency this proton and the RF signal, they match together and there is an exchange of energy. This proton will absorb those energy and they will displace from its alignment. Only when the RF pulse and the proton have the same frequency, proton can pick up some energy from the radio waves, and this phenomenon is called resonance, and that frequency is known as Larmor frequency. So, as we understood, once this RF signal has been cut or they are at a resonance with this proton, then they will absorb some energy, and this longitudinal energy, that magnetic field will be reduced, the component will be reduced, and another transverse transverse field will be introduced, or magnetization will be introduced. These are the radio waves has two effects. It lifts some protons to higher level of energy, and it also causes the proton to precede in steps in phase. The former result in decreasing the magnetization along z axis, as I have shown here, the so called longitudinal magnetization. So that means application of RF pulse, if it is in a resonance, then longitudinal magnetization will reduced. Then the latter establishes a new magnetization in xy plane, that is shown here. So a new transversal magnetization which moves around the preceding protons. So these are the two effects that will occur due to the application of RF pulse. As the transversal magnetic vector moves around with the preceding proton, it comes towards the receiver antenna, goes away from it. So what will happen? Once this RF pulse, it will we withdraw that, then what will happen? This transversal magnetic field or magnetization, this will try to come back to their original state, and it will reduce. This transversal magnetization strength will reduce, and longitudinal magnetization strength will increase once we withdraw the RF pulse. But by withdrawing that, what will happen? Once it want to come back to its original state, this transversal magnetization state wants to come back to its original state, or to enhance the longitudinal magnetization, they has to release some energy in form of RF signal, and those RF signal has been cut or has been captured by these antennas or receivers. This is known as the magnetic resonance signal. The precision frequency of a proton depends on the strength of the magnetic field. If the strength is different from point to point in the patient, then proton in different places precedes with different frequencies, and as they precedes with different frequencies, the resulting MR or the magnetic resonance signal from different locations also has a different frequency, and by the frequency we can assign a signal to a certain location. That means different tissue, they have different precision, those protons have different precision frequencies, and due to that the MR signal is also differ from tissue to tissue, which has been captured in the antenna or receiver section of MR machine or magnetic MRI machine. As soon as the RF pulse is switched off, the whole system which was disturbed by the RF pulse goes back to its original state. We call that relaxed state. So here two things will happen. One is the transverse magnetization starts to disappear, because due to that application of RF, the transversal magnetization occurs, and when we withdraw that, it will start disappearing. That process is called transversal relaxation. That process is called transversal relaxation, and at the same time the longitudinal magnetization goes back to its original size, because the strength will increase. As it is decreasing, the transverse magnetization decreases, the longitudinal magnetization coming back to its original size. This process is called longitudinal relaxation. The protons that were lifted to a higher energy level due to the application of RF signal or RF pulse now go back to their original state, which is at lower energy state, by releasing the RF signal. Okay. So, the longitudinal magnetization increases again. This longitudinal relaxation is described by a time constant T1. So, the longitudinal relaxation time, the transversal magnetization decreases and disappears. This transversal relaxation is described by a time T2. So, we have two times. One is your relaxation time for longitudinal magnetization, another one is the relaxation of transversal magnetization. So, that is T1 for longitudinal relaxation, T2 for transversal relaxation. T1 is longer than T2 because immediately as we draw that RF signal, that transverse magnetization disappears within very few time period. So, that is T2. So, in general the T1 is longer than T2, means the longitudinal relaxation time, it takes more time than this transversal magnetization or relaxation period. And just to give you idea, T1 is about 2.5 to 10 times as long as T2. So, T1 is defined as the time when about 63% of the original longitudinal magnetization is reached, and T2 is the time when the transversal magnetization decreased to 37% of the original value. So, you have this curve. So, as it is a 63% for original, we call that the time, and 37% for this T2. Water has a longer T1 than fat, and T2 of water is longer than T2 of impure liquid contain larger molecules. This is the MRI block diagram where you can say the patient is lying in between a permanent magnet and for alignment. Then to create a gradient in this different magnetic field in different directions, like in x direction, y direction and z direction, we have electromagnets like x gradient power, y gradient power and z gradient power. They are electromagnets. And we have some RF generator, radio frequency generator, then that signal has to be passed through the radio frequency power amplifier and transmitted through this transmitter coil, or we can say just like an antenna. It is passing, this signal will pass through the patient, and again that T1, T2 relaxation time will come when we withdraw that signal, and that will also release some energy in RF signal that has been captured by this received coil, and equivalent current will send as a pre-amplifier and then received, and the signal will be sent to the interfacing computer, and computer will process that and display that. This is the simple block diagram explaining the working principle of magnetic resonance imaging. There is a magnet which provides a strong, uniform, steady magnetic field, that is B naught. Normally it is like in between from 1.5 to 1.5 to your 3 or 7 Tesla, this magnetic field. The superconducting magnetic coils are cooled to liquid helium temperature and can produce very high magnetic field for the permanent magnet purpose, for initial alignment of the protons in our patient body. Hence, signal to noise ratio of the received signal and image quality are better than the conventional magnets used in MRI. So, basically magnets are used to reduce the signal to noise ratio for a better quality imaging. Different gradient coil system produce a time varying controlled spatial non-uniform magnetic field in different direction in X, Y and Z direction. The patient is kept in the gradient field space. There are also transmitter and receiving RF coils surrounding the site on which image to be constructed. So, as we have discussed previously, the same thing has been written here. When this superposition takes place, the resonance frequency of the preceding nuclei will depend on the position projection of the structure of the three-dimensional objects. By taking a series of these projections at different gradient orientation using X, Y and Z coils, three-dimensional images can be obtained. The slice of image depend upon the gradient magnetic field. The gradient magnetic field is controlled by computer, and that field can be positioned in three different planes as we have shown, X, Y, Z. The transmitter provides the RF signal pulse, and the receiver nuclear magnetic resonance signal is picked up by the receiver coil and fed for signal processing. By two-dimensional Fourier transform, we are using Fourier transform as a tool to create or to reconstruct the image in the computer for display. Now, there are some advantages as we have previously discussed. There is no ionizing radiation in this MRI. They are very high contrast between different tissues, soft tissues, and cross-sectional images without any orientation. We have offer potential for physiological imaging also. So, you can mark the relaxation period of T1 and T2 for different tissues, which will the basic fundamental of imaging or contrast in different areas. That for like adipose tissue, the T1 it is millisecond, it is 240 to 250, and in T2 is 60 to 80. As we have discussed, it is approximately 2.5 to 10 times of this T2. T1 is more. So, next we will see some of the formulas and numericals related to this. As we have seen, if the mass of the charge is m, then the orbital angular momentum we can say from the formula L equals to mr square omega. Omega is the angular frequency, r is the in the path, the radius of the circular path, and this classic gyromagnetic ratio is defined as the that is the gyromagnetic constant we have calculated there, that here it is shown how it has been derived, that is gamma c equals to mu by L, where mu is the magnetic dipole moment, and from that we can calculate that it will be equals to the gyromagnetic ratio. It is frequency dependent, and also it also depends on this external magnetic field. And the spin state, that is two different states, one is parallel, another is anti-parallel. The energy difference among them is delta equals to h nu. So, this nu h is your Planck's constant, and the physical meaning of this relation is that the photon of energy nu is either absorbed to send an electron to a higher energy state, or it is radiated for the electron to fall to a lower state. So, eventually excited electrons return to their original equilibrium state by radiating that amount of energy, and that radiation frequency is in terms of nu. So, unlike X-ray imaging that emits ionizing radiation, only harmless photons are emitted during this mechanism that is used in MRI. So, these are harmless. So, what is the frequency necessary for this transition? This is known as your Larmor frequency, and Larmor frequency, as we have seen, it is related to this frequency. We can say this is this term FL, we can say FL also we can write. The Larmor frequency is equals to this gamma B naught. Gamma is your gyromagnetic ratio. So that is equals to 42.58 megahertz per Tesla, or in the radian scale you can 2.675 into 10 to the power 8. So this is a constant. So the question is, find the pulse length necessary to achieve a phase rotation of pi by 2 for the magnetic field in Tesla, given in Tesla, induced at 15 millimeter from a wire carrying 30 ampere of current. If this is wire, so we need to 15 millimeter from a wire carrying a current of 30 ampere. This current, this is your 30 ampere. Now we'll see. Magnetic field is given by, this is your Biot-Savart law. So here magnetic field can be calculated. Field intensity B equals to mu naught I by 2 pi r. So mu naught is a permeability, I is the current, 2 pi r is this, r is this one. So here B can be calculated because we know mu naught, which is equals to 4 pi into 10 to the power minus 7, and current is given 30 ampere, and this radius is also given, that is your 15 millimeter, or it is 0.015 meter. So this is the amount of magnetic field applied. Now we need to find out the Larmor frequency. So this Larmor frequency is related to this equation, omega, or F, you can see F equals to gamma B. B is 4 into 10 to the power minus 4 Tesla, and gamma we know that is equals to, in the radian, it is given in the previous slide, you have seen it is 2.675 into 10 to the power 8, and now you can multiply these two to find out what is the frequency, Larmor frequency. So we found for this condition the Larmor frequency is found to be 1.07 into 10 to the power 5 radian per second. Now the question is, find the pulse length to achieve that phase rotation of pi by 2, and now we have this Larmor frequency, we have the phase to change. The formula for phase rotation, we know that the phi equals to omega t. We know this omega, and t can be calculated. For solving for t, phi by omega, phi is pi by 2 radian. So phi is given. For pi by 2 rotation, we have to find out the time period. So this pi by 2 divided by omega, that is your frequency, as we have calculated, 1.07 into 10 to the power 5 radian per second. So simplifying that, we found the time period required, or this relaxation time, is equals to 1.47 into 10 to the power minus 5 second. This much of time required to rotate the dipole moment of this proton, or rotating proton of pi by 2 is equals to 1.47 into 10 to the power minus 5 second. The next question is, what are the Larmor frequency expressed in megahertz for B field is equals to 1.5. That means B is given equals to 1.5 Tesla. Okay, and we know that this gyromagnetic ratio is equals to 42.58 megahertz per Tesla. So by multiplying this, we found that the Larmor frequency is equals to 63.87 megahertz. So this type of question may be asked. So these are all about basics of MRI. Thank you.